Your lungs exchange gases through simple diffusion and don't actually care whether oxygen comes from air or liquid. This isn't science fiction anymore. In 1998, researchers kept premature lambs stable for hours using perfluorocarbon ventilation, proving that lungs can process oxygen dissolved in liquid at concentrations of 35 to 70 milliliters per 100 milliliters of fluid. In 2025, this liquid breathing technology has advanced to the point where the physiological barriers are becoming understood and potentially solvable. While the deepest scuba dive still maxes out at 332 meters and requires 15 hours of decompression, liquid breathing could theoretically eliminate decompression sickness entirely. The question isn't whether the basic physiology works, but what technological and human factors still stand between us and the deep ocean. Yet even as this breakthrough approaches, we remain constrained by limitations that have persisted for decades. The 2025 Deep Sea Challenge. The numbers tell the story of human limitation underwater. Current scuba diving records max out at 332 meters, while saturation diving reaches 701 meters, both achievements that haven't been surpassed in decades. These barriers exist not from lack of courage or equipment, but because physics creates an insurmountable wall when breathing compressed air at extreme depths. Every breath floods the body with compressed gases that create deadly complications during ascent, making deeper exploration impossible with current methods. Meanwhile, industrial operations have pushed far beyond human reach. The Perdido oil field operates under nearly 2,450 meters of ocean, requiring constant maintenance that no human diver can provide. Deep-sea mining operations target polymetallic nodules on abyssal plains at depths exceeding 4,000 meters, where critical rare earth elements essential for renewable energy technology lie scattered across the ocean floor. These operations require precision work that only human hands and judgment can provide, yet they exist in a realm completely inaccessible to human divers. The economic stakes have grown astronomical. Current estimates place the value of untapped deep-sea mineral resources at over $16 trillion, with lithium deposits alone worth enough to power the global transition to renewable energy. Offshore wind farms now extend into waters deeper than 800 meters, requiring constant maintenance and repair work that pushes the boundaries of what remote-operated vehicles can accomplish. Each day that these depths remain inaccessible to human workers costs the industry millions in lost efficiency and delayed projects. Atmospheric diving suits represent the current best attempt to bridge this gap. These mechanical systems maintain internal pressure at 1 atmosphere while protecting the occupant from crushing external forces. However, they weigh over 500 kilograms, move with limited dexterity, and cannot safely operate beyond 600 meters. The bulk prevents access to confined spaces where much critical work must be performed, and suit failure at maximum depth means almost certain death. Remotely operated vehicles have advanced significantly, with AI-enhanced control systems reaching record depths. However, these machines lack the intuitive problem-solving ability that human presence provides. Complex repair work, unexpected equipment failures, and delicate operations still require human judgment and adaptability that no remote system can replicate. The communication delay between surface operators and deep-sea RO creates additional complications, with even minor adjustments taking precious minutes to execute. The gap between human capability and industrial necessity has created a technological bottleneck that threatens to limit humanity's expansion into Earth's final frontier. Ocean mining companies report that the inability to place humans at work in depths costs them an estimated 40% efficiency loss compared to shallow water operations. Maintenance crews struggle with underwater installations that were designed for human servicing but remain perpetually out of reach. Scientific research expeditions miss critical discoveries because certain types of specimen collection and in situ analysis can only be performed by human researchers. The root cause of this limitation isn't the crushing pressure itself, but specifically the act of breathing compressed air under extreme pressure. The human body can theoretically withstand enormous pressures when properly supported, as demonstrated by atmospheric diving suits and submersibles. The problem emerges when humans must breathe gases that become compressed to dangerous densities. Each breath at depth contains exponentially more gas molecules than surface breathing, saturating body tissues with nitrogen and creating the conditions for decompression sickness, nitrogen narcosis, and oxygen toxicity. This realization has led researchers to question a fundamental assumption about human underwater survival. What if the solution isn't better air delivery systems or more sophisticated decompression protocols? What if humans don't need to breathe air at all? The concept challenges every instinct about human survival, but the physiological reality suggests something remarkable about how our respiratory system actually functions. Recent advances in liquid breathing research have moved this concept from theoretical possibility to practical development. Scientists have identified specific liquids that can carry dissolved oxygen and carbon dioxide in concentrations sufficient to support human life. These perfluorocarbon compounds demonstrate the ability to facilitate gas exchange through lung tissue while remaining chemically inert and non-toxic to human physiology. Laboratory tests with animal subjects have proven that mammals can survive extended periods breathing oxygenated liquids, with successful gas exchange occurring throughout the process. The breakthrough potential of liquid breathing technology extends far beyond solving current depth limitations. Liquids are incompressible, meaning a human breathing liquid would experience no pressure differential between their internal and external environment as they descend. The crushing pressure that creates decompression sickness, nitrogen narcosis, and oxygen toxicity will become irrelevant because the breathing medium wouldn't compress or decompress during depth changes. This could theoretically allow humans to descend to any depth where their physical structure could withstand the external pressure. The implications stagger the imagination. Human explorers could potentially reach the deepest ocean trenches, working directly at depths that currently require only the most sophisticated submersibles. Deep-sea mining operations could employ human workers at any depth, revolutionizing underwater industry and making previously impossible projects economically viable. Scientific research could advance exponentially with human researchers able to work directly at the bottom of the ocean, collecting samples and making observations that no remote system could replicate. The technology exists. The principles have been proven in laboratory settings. Yet the concept feels impossible to most people because it challenges the most basic assumption about what breathing means and how human survival works underwater. While your lungs don't care what you breathe, the physiological reality behind this challenge reveals something remarkable about human respiratory function. Your lungs are not air-breathing organs designed specifically for atmospheric gases. They are gas exchange organs that facilitate the transfer of oxygen into your bloodstream and the removal of carbon dioxide from your body. The specific medium delivering these gases is completely irrelevant to the lung tissue itself, as long as the exchange process can occur effectively. The alveoli in your lungs are microscopic sacs that serve as the interface between your respiratory system and your circulatory system. These tiny structures contain walls so thin that gases can pass through them directly into surrounding blood vessels. When you inhale, oxygen crosses these membranes and binds to red blood cells, while carbon dioxide moves in the opposite direction from blood to lung cavity for removal during exhalation. This process depends entirely on concentration gradients and molecular diffusion, not on any special properties of atmospheric air. Each alveolus functions like a biological filter that selectively allows certain molecules to pass through while blocking others. Oxygen molecules are small enough to cross the alveolar membrane and have chemical properties that allow them to bind with hemoglobin and red blood cells. Carbon dioxide molecules can cross in the reverse direction because they exist in higher concentrations in blood than in the lung cavity. The membrane doesn't distinguish between oxygen delivered by air versus oxygen delivered by any other medium, as long as the concentration is sufficient to maintain the necessary gradient for transfer. Think of your lungs like a factory that processes raw materials into finished products. The factory doesn't care whether trucks, trains, or ships deliver the raw materials, as long as the materials arrive in the right quantities and quality. Your alveoli function the same way with oxygen delivery. They extract what they need from whatever medium fills the lung space and ignore everything else about that medium. The surrounding infrastructure of airways, bronchi, and respiratory muscles simply moves the medium in and out to facilitate this exchange process. This principle already operates in human development before birth. Fetuses breathe amniotic fluid until birth. Proven lungs work with liquid mediums, not just air. The developing respiratory system functions normally throughout pregnancy with lungs completely filled with fluid. The transition to air breathing only occurs after birth when the liquid is expelled and replaced with atmospheric gases. This demonstrates that human lungs possess inherent capability to handle liquid environments from the earliest stages of development. The amniotic fluid example proves that the alveolar walls can maintain their selective permeability, whether they're in contact with gas or liquid, as long as the liquid contains adequate dissolved oxygen concentrations. This isn't a special adaptation that disappears after birth, but rather a fundamental property of lung tissue that remains throughout life. Most adults never experience this capability because they never encounter situations where breathing liquid becomes necessary or beneficial. Medical research has demonstrated that various other mediums can support gas exchange through lung tissue when properly formulated. Scientists have tested different liquid compounds to determine which ones can carry sufficient oxygen while remaining biocompatible with human physiology. These experiments consistently show that the lungs themselves adapt readily to processing liquid mediums with gas exchange rates that can match or exceed those achieved with atmospheric breathing under certain conditions. The psychological barrier to accepting liquid breathing stems from deeply ingrained survival instincts rather than physiological limitations. Every human learns from infancy that liquid in the lungs means drowning and death, creating powerful mental associations that persist regardless of rational knowledge. This instinctual response makes the concept feel impossible even when presented with scientific evidence of its feasibility. The fear response to liquid-filled lungs exists independently of actual physical danger, creating a mental obstacle that can be more challenging to overcome than the technical aspects of implementation. Evolution programmed humans to associate liquid in airways with mortal danger because throughout most of human history, this association was completely accurate. Water entering the lungs typically meant drowning, so developing strong aversion responses improved survival rates. However, this evolutionary programming doesn't distinguish between harmful liquids like water and potentially beneficial liquids specifically designed to support respiratory function. The panic response activates regardless of the liquid's actual properties or safety profile. Understanding that liquid breathing doesn't require change in lung function helps clarify why the concept works in principle. The respiratory system doesn't need modification or adaptation to process liquid mediums because it already possesses all necessary capabilities. The challenge lies in identifying liquids with appropriate properties for oxygen transport and carbon dioxide removal, not in somehow altering human physiology to accommodate liquid breathing. This distinction is crucial because it means the solution involves engineering better breathing mediums rather than changing human biology. The key breakthrough in liquid breathing research involves finding compounds that can dissolve large quantities of both oxygen and carbon dioxide while remaining safe for prolonged contact with lung tissue. These liquids must maintain stable chemical properties under pressure, resist contamination by body fluids, and avoid toxic effects on respiratory membranes. The liquid essentially needs to function as artificial blood that operates in the lung cavity instead of blood vessels, carrying gases back and forth between alveoli and the external environment. Scientists have been investigating these possibilities for over 50 years, testing various chemical compounds to determine their suitability for respiratory applications. Research efforts accelerated significantly when medical applications emerged for treating severe respiratory diseases. Doctors found that certain liquid ventilation techniques could help patients with damaged lungs by providing more efficient gas exchange than conventional mechanical ventilation. These medical applications provided crucial data about how human lungs respond to liquid breathing under controlled conditions. Current research focuses on perfecting liquid formulations that can support human life while addressing the practical difficulties that have prevented widespread adoption. Scientists have identified specific chemical compounds that show exceptional promise for human liquid breathing applications. The foundation exists for understanding why lungs can process liquid mediums, but the real breakthrough lies in understanding why current breathing methods create such deadly limitations at depth. The pressure problem that kills divers. Compressed air becomes a deadly cocktail when humans breathe it under extreme pressure. Every single breath taken at depth floods the body with exponentially more gas molecules than the same breath would contain at the surface. At 100 meters depth each, breath delivers 10 times more nitrogen and oxygen molecules than surface breathing. At 300 meters, that number jumps to 30 times the normal concentration. This massive influx of compressed gases creates a cascade of physiological problems that become increasingly dangerous as depth increases. 3 core hazards emerge from breathing compressed air at depth: nitrogen narcosis, decompression sickness, and oxygen toxicity. Each driven by pressure. Forced increases in gas partial pressures. Nitrogen narcosis demonstrates how compressed air becomes toxic to human consciousness at relatively shallow depths. Nitrogen normally exists as an inert gas in atmospheric air, making up roughly 78% of every breath without causing any noticeable effects. However, When nitrogen gets compressed under pressure, it begins to act like an anesthetic agent, dissolving into fatty tissues throughout the body and particularly affecting brain cells. Divers typically begin experiencing symptoms around 30 meters depth, where thinking becomes clouded and decision-making abilities deteriorate. By 60 meters, the narcotic effect becomes severe enough to impair motor coordination and judgment. Decompression sickness, known as the bends, presents the most lethal consequence of breathing compressed air at depth. Consider the case of a commercial diver working at 90 meters who experiences rapid ascent due to equipment failure. The nitrogen that dissolved harmlessly in his tissues under pressure suddenly attempts to return to gaseous state as pressure decreases. Instead of being safely eliminated through the lungs, the nitrogen forms bubbles within tissues and blood vessels. These bubbles can block blood flow, causing severe pain in joints and muscles, or form in the spinal cord, causing paralysis. More critically, bubbles can enter the arterial blood system and travel to vital organs, creating arterial gas embolism that proves fatal within minutes. The severity of decompression sickness depends entirely on how much nitrogen has dissolved into body tissues during the dive. Longer dives at greater depths create higher nitrogen saturation levels, requiring correspondingly longer decompression times. Deep saturation dives can require decompression periods lasting several days, with divers making carefully timed stops at specific depths to allow nitrogen to gradually leave their systems without forming dangerous bubbles. Oxygen toxicity creates the third major hazard when breathing compressed air at extreme depths. While oxygen is essential for life, breathing compressed air at depth delivers oxygen at partial pressures far exceeding normal atmospheric levels. At depths beyond 60 meters on regular air, the partial pressure of oxygen reaches levels that become toxic to human physiology. Oxygen toxicity initially affects the central nervous system, causing symptoms ranging from nausea and dizziness to tunnel vision and seizures. At extreme depths, oxygen toxicity can trigger sudden unconsciousness and convulsions that prove fatal underwater. Current technical diving solutions attempt to manage these problems through gas mixture manipulation rather than elimination. Trimix replaces some nitrogen with helium to reduce narcosis effects while limiting oxygen percentage to prevent toxicity. Heliox eliminates nitrogen entirely for the deepest dives, using helium as the inert gas component. These mixed gas approaches allow deeper diving by reducing the severity of each individual hazard, but they cannot eliminate the fundamental problem of breathing compressed gases under pressure. Even the most sophisticated gas mixtures only postpone the inevitable limitations imposed by pressure physics. Helium creates its own narcotic effects at extreme depths, causing high-pressure nervous syndrome that produces tremors, cognitive impairment, and motor dysfunction. Helium also conducts heat much more efficiently than nitrogen, causing rapid body heat loss that limits dive duration. Most importantly, helium must still be decompressed carefully during ascent, often requiring even longer decompression schedules than nitrogen-based breathing mixtures. Saturation diving represents the ultimate expression of current compressed air technology, yet even this approach cannot overcome the fundamental physics involved. Saturation divers live in pressurized chambers for weeks at a time, allowing their tissues to become completely saturated with breathing gas so that no additional gas absorption occurs during working dives. This eliminates the need for decompression between individual dives, but requires a massive decompression process lasting several days when the saturation period ends. The technique allows extended work at depth, but still cannot safely exceed the 701-meter record established decades ago. The core issue remains that all current diving technologies require humans to breathe gases that compress under pressure. Whether using air, trimix, heliox, or exotic, gas mixtures, the fundamental physics of gas compression creates unavoidable physiological hazards that worsen with increasing depth. These aren't engineering problems that can be solved through better equipment or improved techniques, but rather fundamental limitations imposed by the behavior of gases under pressure. Liquids behave completely differently under pressure than gases, remaining essentially incompressible regardless of depth. However, liquid breathing faces its own formidable challenge that has prevented practical implementation. Perfluorocarbon density measures approximately 1.9 grams per milliliter compared to air's 1.2 milligrams per milliliter. Moving liquid through a 6-liter lung capacity requires displacing roughly 12 kilograms per breath. No human respiratory muscle can sustain a 12-kilogram tidal load, even at rest, let alone during exertion. Early animal experiments with liquid ventilation consistently demonstrated this limitation. Test subjects died of carbon dioxide buildup because their respiratory muscles couldn't maintain adequate liquid circulation for gas exchange. The animals could absorb oxygen from the perfluorocarbon liquid, but couldn't exhale carbon dioxide efficiently enough to prevent fatal accumulation. This mechanical limitation makes clear that liquid breathing requires external assistance rather than relying on natural respiratory muscle function. Despite these mechanical challenges, incompressible property of liquids means liquid breathing could theoretically eliminate all three major diving hazards simultaneously while allowing humans to reach previously impossible depths. The question becomes whether technology can overcome the physical limitations that have prevented liquid breathing from moving beyond laboratory experiments. Economic pressure to solve this problem has never been greater, as industries worldwide face mounting costs from humanity's inability to work at the depths. The 2025 resources and infrastructure now exist. The underwater economy has exploded into a multi-trillion-dollar sector that demands human presence at depths far beyond current diving capabilities. Deep-sea mining operations target the most valuable resource deposits on Earth, scattered across abyssal ocean floors at depths ranging from 3,000 to 6,000 meters, completely inaccessible to human workers using current technology. The numbers driving this underwater gold rush are staggering. According to 2025 Deloitte analysis, cobalt demand could exceed currently known land-based reserves by 423% by 2050, with similar shortages projected for nickel and lithium. These minerals are essential for batteries, renewable energy systems, and advanced electronics that power the modern economy. The solution lies in massive polymetallic nodule fields in international waters that contain more cobalt than all terrestrial mines combined. These potato-sized formations carpet vast areas of the Pacific Ocean floor, formed over millions of years through complex geological processes. The nodules contain not only cobalt, but also nickel, copper, and rare earth elements that are becoming increasingly scarce on land. Mining these deposits requires precision extraction techniques that can separate valuable materials from seafloor sediments without causing excessive environmental damage. Current remotely operated vehicles lack the dexterity and real-time decision-making ability needed for efficient nodule collection at these depths. Companies like Deep Green Metals and Global Sea Mineral Resources have invested billions in developing extraction technology for depths that exceed human diving limits by factors of 10 or more. These operations require constant maintenance, equipment adjustments, and quality control measures that are extremely difficult to accomplish using remote systems alone. The nascent deep-sea mining industry involves various sectors, including dredging companies and offshore drilling contractors, with traditional mining companies expected to become involved as well. Offshore renewable energy installations are pushing into deeper waters as coastal areas become saturated with existing wind farms. Floating wind turbines now operate in waters exceeding 800 meters depth, requiring regular inspection, maintenance, and repair work that becomes exponentially more challenging as water depth increases. These installations need constant human oversight for complex maintenance procedures that automated systems cannot handle effectively, yet they exist far beyond the reach of current diving technology. Remotely operated vehicles represent the current state of the art for deep-sea industrial work, but their limitations become more apparent as operational depths increase. IEEE and deep studies confirm that ROVs operating at 6,000 meters depth still lack fine manipulation capabilities essential for precision work. The most advanced systems suffer from communication delays, limited manipulator dexterity, and inability to adapt to unexpected situations. Tether ROVs require constant connection to surface vessels, creating logistical complications and weather dependencies that can halt operation for days or weeks. Video feeds from underwater cameras suffer from limited visibility, color distortion, and perspective problems that make fine manipulation extremely difficult. Haptic feedback systems attempt to provide tactile sensations for ROV operators, but current technology cannot replicate the sensitivity and adaptability of human hands. ROV operators require extensive training to perform even basic tasks, and the learning curve for complex operations can take months or years to master. Climate change research demands human presence at depths where critical oceanographic processes occur, but remain largely inaccessible to direct human observation. Deep water coral ecosystems exist at depth between 1,000 and 4,000 meters, harboring biodiversity that scientists are only beginning to understand. These environments require careful sample collection, in situ experimentation, and real-time observation that remote systems cannot provide with sufficient precision.